Okay, so let's sort of continue, right? And we were into the design of a convergent divergent nozzle, right? For a given exit Mach number, right? And what we said was that it's a minimum length nozzle. That is when the flow comes into the throat area, which is the sonic area, then it expands, right? And this expansion is not over a length, right? It could be over a length, right, as it is in like wind tunnels, but then we decrease that length to a point so that we have a centered expansion wave, right? And that's really the minimum length you need so that if the flow diverges, and then finally we get parallel uniform parallel flow to the walls of the nozzle. So that's where we were. Okay, so let us sort of go ahead and do that. Okay, and what we said was that, so basically what we're going to do is that we have to design a nozzle like that, right? And of course we said that we're also going to take the line of symmetry. Okay, this is a line of symmetry, so as long as we just calculate in one part, we can get it for the other, right? Okay, so basically this is going to be repeated. So at this particular point of time, so this is the sonic region, right? This is the sonic region, this is the throat, right? And what we know here is the exit Mach number. So the exit Mach number is given as 2.4, right? This is the problem. So therefore what we calculated is the maximum angle here, right? This was the maximum angle here, and this was theta max, right? And we were able to calculate that as right. So which is the Prandtl-Meyer function with respect to the exit Mach number, half of that. So that is your theta max. So that is all the information we have. What we don't have right now is this contour, and this is something that we need to design. We need to say where, you know, various points of this surface is going to be located. So that's what our problem is. So what we said was, therefore, that essentially we have a centered expansion wave. Say we're going to call this, say, let's give this some name. Okay, we're going to call this, say, A. Let's call this point, say, A, right? And so let us basically we have an expansion fan going from here. Okay, so now okay, so what we basically have is 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6. Yeah, I think that should work. So what I have essentially drawn over here is an expansion fan. Okay, now what is happening is this thing is and we'll have a similar point down here, right? So because this is, I have just taken the symmetric part of it, so I will have one more over here. So similarly, I have, say, at this particular point B out here, right? If I have a, so let's just cut that there, right? So so at this point B, we will have a similar expansion fan, right? We'll have a similar expansion fan. Okay, so when we have that, so then for these are going to interact, and then what are you going to get is this. okay, and so on and so forth, right. So therefore, what we're going to do is just ignore this bottom part of it and just consider this. Okay, so essentially we'll have one more like that. Okay. Okay, so that's what we're going to have. Okay, so we're going to pretty much have all this, and this is also generating from here. We are not going to look at this. Okay, so this is how the expansion fan is going to look like, and if you ask, so now let's do the next thing to do out here. Now, once we draw this sort of an expansion fan, what you essentially see over here is that this is actually a grid. Right, but this is a special kind of grid because what we have is these are left running characteristics, the red ones and pink ones, and the blue ones are essentially right running characteristics. And we know from our analysis the last couple of lectures that there are certain relations called compatibility relations which are valid on these characteristics, right. Okay, so now the next thing to do here is to say number these points, okay, where these are intersecting. So if I had to do that, so I'm going to call this as say 1, okay, this is 2, this is 3, 4, 5, 6, 7, right. Right. Now, just remember at this point of time that we haven't actually, we don't know where this point 8 is at this point of time. We have to find out where this is. Okay, 8, and then again we come back in here, so say 9, 10, 11, 12, 13, 14, 15, and so on and so forth. We're sort of going on each characteristic and labeling it. So we come back in here, so 16, 17, 18, 19, 20. So we got say 21. We come back in here, 22, 23, 24, 25, say 6. Come back in here, 27, 28. That's it. Okay, so essentially, so what you can see from here, if you now just sort of take a look back here, what we have to do here is to design this nozzle, which means I need to find locations of various points on the surface, and I have basically 1, 2, 3, 4, 5, 6. When I consider an expansion fan with as many Mach waves out here, which is say 1, 2, 3, 4, 5, 6, 7. Okay, including the, if I have like, if I'm considering a wave front, which I'm dividing into say 8 divisions, I have 7 Mach waves going in here, then I have essentially 1, 2, 3, 4, 5, 6 points on this surface. So I should be able to locate these points with respect to this, and hence when I connect them, I will have a surface. So clearly, obviously, if you can have more number of points here, more number of points within this here, etc., etc., then it gives a better estimation of the nozzle. So for that, all you need to do is take more and more number of Mach waves. As you can clearly see that from here. Right. So hence computational task will be more efficient if you write a computer program, and then if we do this, we can do this better, right. Okay, now so therefore I've taken this just to kind of run you through the actual procedure through which we're going to do this, right. So let us go step by step. So what we have found out over here is our theta max, right. So our theta max is therefore Prandtl function right, and this is 18.375. I think we did this. Okay. Now the thing is, how we locate these Mach waves is really up to us. Okay, this is arbitrary. This is really up to you. I've taken like 8 or yeah, 1, 2, 3, 4. Yeah, I've taken like 7 Mach waves out here. So you can take 100, you can take 200. You know, it'll give a better estimation of that. So at this point, so this is really up to us. How we orient this is really up to us. So what we said was last time. So this is my theta max. So now let this angle A1. Okay. So let us say let me just develop a table. So let us say this is the left running characteristics, right, and we have the theta, corresponding theta, right. So for A1, okay, so for A1, let's say we will take as 0.375. Okay, so what we 0.375. So what we are left out with is essentially 18 degrees, which we will divide amongst this, which is 1, 2, 3, 4, 5, 6. So 3 degrees each, right? So therefore, what we'll do is, this is say within the fan, okay, delta theta within the fan. So let's write it this way. So within the fan, delta theta is 18 by 6 degrees. So therefore, for the characteristics, say A9, okay, A9 theta is going to be delta theta, which is 3 degrees. Okay. So again for A16, so we're considering A16 here. So then what we get there is A16, it is 0.375. Okay. Then similarly for say A22, it is and so on and so forth. So again for say 27, you have 4 times, 5 times, and 6 times, right? So so essentially, so so let's say A34, okay, A34. Therefore, this is so this is 3, so 4, 5, 6. Right. So, and you can see this gives 18.375. So, this is 18.375. Okay. So, now that so basically we've calculated the thetas for each of these characteristics. So, what essentially we can say therefore is that this 0.375. Now, let us look at these each characteristic separately. Now, if you look at this characteristic, so this has a theta of 0.375, which means this is equal to theta 1. This 0.1 is on this characteristic. So, this is corresponding to the theta of theta 1. Similarly, for this characteristic, the theta is is 3.375 A9. So therefore, theta 2 and theta 9 are the same, right? So this corresponds to and so on and so forth. So similarly, 16. So you have so theta 3, theta 10, and theta 16, right? So then here you have right. So similarly for here you have theta 4, theta 11, theta 17, and theta 22, and so on and so forth. Okay. So having done that, now let us see how we can use what we're going to basically do now is going to apply our compatibility equations, and what we saw from last time, right, is that for C minus characteristics, we have theta plus mu, which is equal to constant, and for C plus characteristics we have theta minus mu, which is constant, right. So therefore, okay, so now what we will do over here is that let us say look at this characteristic. Okay, let us look at this characteristic, the right running characteristic at 1. Okay, so the characteristic which is, say, what we're going to look at now is this characteristic. So 1, 2, 3, 4, 5, 6, 7 and 8. So let us look at this right running characteristic. Okay, now if we do that, we know it's a right running characteristic. So theta minus mu is a constant, right? Theta minus mu is a constant. So basically now on this right running characteristic, we will say consider points 1 and 2. Okay, and apply the compatibility equation between these 2 points. Now let's see. So what we're going to do here is the right running characteristics, okay, between points 1 and 2, right? Yeah, between points 1 and 2. So then what we get here is right. So this is my compatibility equation, because on this C plus characteristic, theta minus mu is a constant, right. Now look at this angle. This angle is like 0.375, which is like nearly 0. So now what we are saying is that the flow which is coming in here, right, flow which is entering here is sonic, right. So therefore the Prandtl-Meyer function for that is 0, isn't it? So therefore mu 1, okay, so mu 1 out here is equal to theta 1. So which means that this is 0, which means that theta 2 is equal to mu 2. Okay, theta 2 is equal to mu 2 on this characteristic line, on this characteristic line. So theta 2 is equal to mu 2, theta 1 is equal to mu 1. Now let us do that at, say, now let us consider, say, points 2 and 3. Okay, so if I consider again C plus, right, between 2 and 3. Okay, so what we get is theta 2 minus mu 2 is equal to theta 3 minus mu 3. Now we've just found out that theta 2 is equal to mu 2. So therefore again this means that theta 3 is equal to mu 3, and so on and so forth. So what we see is that in this particular characteristic line 1, 8, so this characteristic line, at each point theta is equal to the Prandtl-Meyer function, corresponding to the Prandtl-Meyer function, right. Now having now if we do that, now let us now come here to the point 8, okay, on the same characteristic line. So now we are at this particular point 8, which is the point which we actually need to design. Okay, so if we come there, so let's say now, okay, let's go here. So again C plus, okay, between points 7 and 8. Okay, so what we have is right. So yeah, so as you know, we found out that theta 8 is equal to mu 8. Theta 8 is equal to mu 8, right. Now the point is how do we locate this? Now theta 8 and mu 8 both are unknown. Okay. Now let us say here, okay, that finally when we do a computer program and do this, we are going to have many more such characteristics. We should be able to do that. So therefore this point will actually probably get closer to this. Okay. In this particular problem I have sort of exaggerated that, okay, just to sort of walk you through the procedure of doing this. So therefore let us say that the point A is connected by a straight line to this point 8. Okay, it's connected by a straight line, A and 8. Okay, so essentially what I'm saying is, so say we have a point A over here, okay, and if I draw a tangent to the curve at A, it makes theta max. Okay, and I'm saying that I'm going to draw a curve. I'm going to draw a curve through this point A, right? That is my job out here. So what I'm saying is that I will take a point here, okay, which is, say in this case point 8, which lies on the same tangent which goes through A, which is we are going to connect A and this point 8 by a straight line, which means what? Which means that this 2 is also theta max. Okay, we're going to connect it by a straight line, right? So therefore, so let us say that theta max, right? So the which is 18.3375, right? So therefore now if I sort of do that, so now what we will need to do is to locate this point 8, right? We will need to locate this point 8. So what we will do is we will just sort of so theta max out here is again now theta 8 is again theta max, right? Theta 8. So we have the same straight line going through here, So this is also theta max. So the average slope between A and 8. So the average slope. This is now just geometry, right? So average slope is theta 8, or say theta A, right? So which is what one can calculate from here, right? So we connect essentially, so therefore we connect this by a straight line to this particular point, right? So now if we do that, so essentially what we do is we continue to do this. Okay, we continue to do this, and again once we've done this out here, so now we've been able to locate this point 8. Okay, so then we do the same thing coming back to this characteristic out here. Okay, we come here and do the same thing over here, and then we're going to locate this point, say 15. Now again, how do we, the point is how do we connect 15 and 8? Again, what we will do is we'll say connect that by a straight line. Okay, so say I connect that by a straight line, okay, and then the average slope is going to be theta 8 plus theta 15 by 2. Okay, so say between the surface between, so similarly between the points 8 and 15, right? If we do 8 and 15, what we get is average slope here is and that's it. Okay, so this is pretty much it. Okay, so hence we will be able to find out the point, locate the point 15. Similarly, we go ahead and locate points 21, 26, 30 and 33 and so on and so forth. Okay, so well, that is all actually there is to this this sort of an exercise. So this is actually the procedure. So as such it is simple, but in order to do this in a more efficient manner, it's always advisable we have to write a computer program for this, so that we can get more denser grid, okay, and unless and until we get these points like really close to each other, so then we're connecting these by straight lines, so you can understand, So we'll get these points, so we'll get more and more points so that they're closer to each other. So if you connect them by a straight line, it should give us less error. Okay, the scope for error is very less. So well, that's it. Okay, so we started out with a problem where we had just we said we had to design a minimum length nozzle which has an exit Mach number of 2.4. Okay, so we used just this mathematical method where we said it's going to be a centered expansion wave. So we got a grid something like this, okay, which is a combination of left running and right running waves, and from that information we were able to calculate what will be theta max here, and then we got several points on the surface which we connected by, it's like connecting the dots, right? You connect that by straight lines, and basically what we are armed with is that on this grid, okay, we are solving the governing equations by means of the compatibility equations, right? So on the right running characteristics and left running characteristics, we use the corresponding compatibility equations, and hence we are able to locate points on the surface. Okay, so yeah, so that really is, that's all there is to this problem. Okay, now well, there are essentially several applications of the method of characteristics. So this was one of them. Okay, now let's just see one more application. Okay, and then we'll close. Okay, now for example, so say we have the problem here is that we essentially have a channel. Okay, we have the channel is essentially, it has, the walls are straight, so we have a channel like this, right, and it's going to give us radial flow. It's going to give us radial flow. So we have, say, a supersonic flow coming in. We have the given Mach number, the incoming Mach number is available to us. So the flow comes in and then it diverges and we get like a radial flow out. Okay, so we just need to calculate the properties. Okay, so we have flow coming in with which is essentially diverging. Okay, so if we do that, so essentially what we have here in this particular case is that we have a channel like that. Okay, we really need to be symmetric over here. So I have a channel here like this. Okay, okay, we have a channel here like this. Okay, and okay, and this is diverging by 12 degrees. It is diverging by 12 degrees. Okay, and input Mach number coming in is 1.436. Okay, so how do we go about this? So what we'll do is, so now this is again, this computational space is mine, isn't it? This is for the user defined. So you can obviously, when you write a computer program, you can do more with this. So let's just say right now what we'll do is, so let us define this. So we will have, say, we'll have a center line somewhere, right? Okay, so let us say we will consider these 2 points. So let's say I'm going to call this as A. Okay, I'm going to take a point out here which is 1, and I'm going to take a point out here as 2. Okay, so we will basically take this. Okay. Now what we will do is that what is happening? Basically the flow is expanding, isn't it? So, it is an expansion fan. So, we will draw this expansion fan, and unlike the minimum length nozzle, now it can expand over a length. It is just a channel. So, we do not have to it is not a centered, it is not necessarily a centered expansion width. Okay. So, if we have this now, let us say now at each point we will have an expansion of the, so we will have say the flow going in directions like this. So, say at this particular point, okay, so let us say we will have, okay, something like that, and okay, so let us say we will take say intervals like this, B and C, some length on that, and then and so on and so forth. Then we have a D over here. Okay, I am trying to be as symmetric as possible, but sometimes my artwork is pretty bad. Okay, so then yeah, so then we will go like that. See, there I go. This is supposed to be like really symmetric, right? Which is what I'm trying to do here. Okay, that's how I'm going to do it in a computer program. So, okay, so then correspondingly, so if I go, I'm going to take this point right here and say I have E, okay, and then run another one, say through this point, like that, and then we have another one, say F, right, and I'm going to run that one through this, and so on and so forth. So, we have this. Okay. Now, let us look at this. So, we will have two more from there. Okay. Okay. Now, if I do this, okay, so essentially what is happening is, now if I look at this, okay, if I look at this, so essentially, okay, all right, that goes through there, and we have this goes through to F. So again, and you have one which goes right up to F. Okay, so then you do that, and then similarly, okay, this is like really confusing. Okay, so then we have, say, this goes through, yeah, 2 goes through E. Okay, so we have this series of 2 goes through and goes through to C. Okay. Okay, so I've been as okay, still not, I wish I was a little more, my artwork was a little better. So if this could run a little parallel to these things, I would have it a little better. But anyways, I'm just sort of, trying to be as, symmetric as possible. Okay. So essentially what we start getting is, so, we'll get lines which are sort of parallel. So what we are trying to do here is that the flow will come in and then it will diverge, and we have radial flow. Now let us look at some things here. Now again, okay, before we do that, let us go ahead and number these like we have done before. So we have 1, 2, so let us call this as 3, 4 and 5. Hopefully this will make a little more sense. Okay. 6, 7 and 8, and you got, say, 9, 10, 11, right, 12, 13, 14 and so on and so forth. right. So we have a sort of a non-simple region out here. So several right running and left running characteristics. Okay. Now if we look at this, how are we going to go ahead and solve for this? Okay. So now let us first get the geometry right. Okay, so we said that the entire the total divergence is 12 degrees, right? It is total is 12 degrees. So if I were to do this geometry right, essentially what I have is say I'm going to look at it like this, right? So what I am looking at is essentially, this is my channel out here, right? What I am looking at is like this. So this is the part of the channel. This I am drawing just to show you the geometry part of this. So if I do this, right, so then this total angle is 12 degrees, right. Now I have taken basically 2 points out here. So then I will have one like that, okay. So that now each of this, right, so each of these is 4 degrees, right. So therefore now this is 2 degrees, and okay, you can see my artwork is not it's not symmetric, please bear with me. Okay, so essentially therefore, so this is the streamline, okay, this is the streamline which is kind of going to, you can see that sort of become curved, it's not going to be so, it's going to be a straight line. So bear with me, okay. So I'm going to sort of just run this through. So I will have a streamline, so essentially this point is going to be here somewhere, so 1, 3, 6 and 9. Okay, and then again we'll have this, okay, you can see I'm going to just draw a line like that. So 2, 5, 8 and 13, and that's going to be another streamline. So those are going to be on there. So now this streamline essentially is making 2 degrees, and this is making 2 degrees. The sense is opposite, right. So what we have over here, now let's do the numerics. Okay, let's do the numerics. Again, we are basically going to use the same right running and left running characteristics. Okay. So if we do that, now let us say look at this point 3. Okay, let us look at this point 3. So maybe I will sort of do that here. So this is the point 3. Okay, so at the point 3, this is my point 3. Okay. So here is, so we have, here we have A, okay, and here we have 1, okay, and here we have B, and okay, so that's it. So if we do this, okay, so let us look at the right running characteristic, between 3 and 1, between 3 and 1. So what we are looking at is the C plus characteristic between points 3 and 1. Okay, so therefore, which means that if I look at that, so therefore theta 1, okay, minus nu 1 is equal to theta 3 minus nu 3. So now you of course know that this is at the A and 1, these are at the is the entrance, right, is the entrance. So Mach number is known here, and we also know the theta here, which we know because of the geometry, okay, So therefore theta 1 and mu 1 are known, okay. So theta 1, so theta 1 essentially this, right, corresponds to a Mach number of 1.436, which is around 10 degrees, and theta 1 is 2 degrees, as we just saw from this. This is the geometry definition, right. It is given that the total divergence of this is 12, the channel is diverging by 12 degrees. This is given to us, and since we have taken, basically divided this radial space into 3 parts, so we found out that this is going to be 2, right. So therefore theta 1 is 2, which means that theta 3 minus gamma 3 is equal to minus 8, right. So therefore this, let us say this is, let us just say this is one relationship that we get. So theta 3 minus mu 3 is equal to minus 8, okay. All right, so then this is it. Now next thing what we will do is take a left running characteristic between A and 3, okay. So let us take left running characteristic between A and 3, right. So again and this is my compatibility equation. Right. So now if I have this, now what is theta A and what is mu A? Now mu A is again this, right. So now mu A out here is again mu 1.436, isn't it? So this is again, because this is also at the inlet, so this is also equal to Prandtl function corresponding to 1.436, and this is again around 10 degrees. And theta A, now what we saw from here, theta A is this my wall out here. So as you can see from here, this here is, so therefore theta A is 6 degrees, okay. So 6 degrees, okay. So which means that theta 3 plus mu 3 is equal to 16, right. So let us call this as, so what you basically have here, okay, what you basically have here is these two equations, okay, and you can just eliminate theta 3 and mu 3 from these two equations simultaneously. So what you get from here, okay, so what if you do that, what you get is, so if you eliminate theta 3, so basically from, okay, theta 3 is equal to 4 degrees, okay, and mu 3 is equal to 12. Okay, so therefore we are basically able to find, so now we can find out the properties, okay. Now having known the Prandtl function, so we can correspondingly find out the rest of the properties there. So therefore theta 3, so we take this particular point and we get 4, and theta 3 is 4, and the theta 3 is 4 and mu 3 is 12, right. So yes, right. So therefore the point 3 is done. Now once we do point 3, now let us look at, say, point 4. Point 4 is here, okay. It's on the center line, but let us go ahead and solve for properties at point 4, okay. So similarly, basically we will be solving for other points, okay. I mean, this is a procedure to go about throughout the entire, we basically divided this thing into a grid which is formed by the characteristics, okay. So let us do that. Let us go and see. say for 0.4, right. So let us see what we get. Now at say 0.4, okay, so this is 0.4. Now let us see at, so this is 0.4. Okay, so what do we have here? So we have a set of characteristics passing through that. So then we have a 0.2 over here. Okay, it passes through 2. Okay, and it passes through 1. Okay, and this goes through to 6 and C. That is fine. So here this is what we have, 4 and 1. So now let us look at this. So this is a left running characteristic. So now let us look at the left running characteristic between 4 and 1. If I do that, so this is C minus between four and 1. So what we have is theta 4 plus mu 4 is theta 1 plus mu 1, right. Now theta 1 is 2 and mu 1 is 10, right, which we found from before. So therefore, okay, now so therefore, so this is equal to 12. Okay, this is equal to 12. So let's again call this as say 1, and again what we will do is we will take 2 and 4, right, 2 and 4. So it is C plus. So now we are going to look at the right running characteristic C plus, okay, between four and 2 basically, right. If we do that, then okay. Now again theta 2 here. So now theta 2, okay. Now mu 2 is something that we know again, which is around 10 degrees, right, because again this is at the inlet, right. So this is all at the inlet. So mu 1 mu 2 is all the same. So this is the inlet. Okay. So now theta 2. Now let us come here. Now theta 2, we are looking at this streamline, which is this streamline. So you can see that this angle is just minus 2. Okay, it is on the other side of the center line. Okay, just the sense is different. It's the same as the streamline going through 1. So therefore this is minus 2. So then this is minus 2. So what this becomes is essentially this is equal to minus 12. That's all. Okay, so then we get this, and again we will now solve for theta 4 and mu 4 from here. Okay, if we do that, what do we get? Which is correct, which should be theta 4 is 0, right, because it is on the central line. Okay, theta 4 is 0 and mu 4 is 12. So then now we basically go around doing this for each and every point, and then we can basically find out the properties. So this is another essentially application of this method of characteristics. Okay, divide the space into a certain grid. Okay, this is user defined, of course, and then use the compatibility equations and find out the properties. Okay, so that should be all. Thank you.